Hello, everybody. Dr. Matt Moynihan here. I got a lot of responses to the previous video about the Polywell. And the number one question that people sent me was, what would satisfy me what would give me confidence that the Polywell was going to work? So this is a design of experiment question. And up front, I just want to say that Lockheed-Martin may have already done this. We don't know. I don't know. It's behind a classified wall. They haven't published in a peer-reviewed paper. When I was in my 20s, I would advocate for the Polywell, and the refrain was pretty common. The refrain was, this is going to work. This is totally going to work. The only issue is we haven't seen a well-funded, well-researched, well-staffed, well-supported, evident or experimental campaign to prove that it will work. But it will work. The problem is we haven't gotten the money to try with the right organization. And that's what we said for year after year after year after year. But that's not true today anymore. Because Lockheed did try. I mean, if you look at the Lockheed effort, that ran from 07, 08 to 2019, 2020. I mean, almost 12 years. And they had a large staff. They had anywhere from 5 to 15 people every year. And they had pulse power experts, vacuum experts, diagnosticians, plasma physicists, modeling. They had the people, they had the tools, they had the money, they had the organization behind them. An effort like that, I think 5 to 10 million a year, every year for 12 years, that's well funded. That's well supported. They had all the things they needed. And if they hit a dead end, then this kind of looks like a dead end. But regardless, let's talk about what would be needed to properly prove that the Polywell could work. And what we want to do is we want to answer several questions. Okay, first of all, we want to know, hey, does this diamagnetic trapping effect really work in real life? Not a computer, not on a model, not in a theoretician, in real life, from real data, from a real machine that's robust. And if it does work, I want to answer some basic questions that I've wondered about for years. What is the size of the cusp hole? If there's a cusp with a hole in it where plasma can leak out, how big is it? How much material leaks out? What is the fluency of that? What is the size of that in different conditions, operating conditions, and under different field strengths? Okay, can you shrink it? If you increase the plasma pressure, the plasma density, or the magnetic field, can you make that cusp hole smaller? Okay, these are questions I want to see. Also, what is the skin region? How much of a diamagnetic current forms there? Is the current stable, steady? Can it be stable over seconds, minutes, or longer? And how much current is there? And then what we want is a photograph or image of some kind that shows plasma in this trap. And we also want to know, what is the density of material inside the trap versus outside the trap? Is the trap stable to interchange instabilities or any other kind of instabilities that occur whenever you have a lot of plasma next to a void, essentially, an empty void with nothing in it or very little in it? And then if that's all true, then I want to know, okay, so now it's all stable and steady and held. What happens when you inject fresh material? Okay. Is there a way to inject fresh material where the trap remains stable? Now, for instance, you could inject through a cusp, or you could inject through on the side, or you can inject from a different. Is there a geometry factor there where you can inject? And the other question I want to know is, what happens when you change the geometry of the rings, okay? Basic Polywell is 6 rings in a box, but there are 12 ring configurations, 24 ring configurations. If you go on Talk Polywell, there are a lot of images that people have put together over the years of lots of geometries for this. So what does the machine look like as you change the ring geometry? Does it improve? Does it not improve, etc.? These are all important questions I'd want to have answered. And then on top of that, once that's all done, is it possible to create a highly negative plasma in the center of this system that would allow for plasma or ions to be heated to fusion conditions? Is that possible with the diamagnetic trap? But really, the root of that question is the diamagnetic trapping effect stronger than all the chaotic forces and behavior that would be introduced by a negative plasma? I don't think it is. I think a voltage force between positives and negatives, or chunks of positive and negative material, is so strong that it just rips apart everything else. And I also think that diamagnetic, if the wiffle ball effect occurs as advertised by Bussard and others, I think it's going to be so unstable that when you inject in material, it might rip the thing apart. Okay? So that's another question that needs to be answered. So these are all the questions that I'd love to see. So how do we answer these questions with data, experimental data from a real live machine, not a model, not a hypothesis, not a theory, real data? That's what we need to get at. So let's talk about the experiment that should happen. I want to talk first about the machine itself, so the engineering and design and construction of that machine. Then I want to talk about how you would create plasma and send it into it. Then I'm going to talk about the diagnostics, the tools that we would use to measure behavior. Okay, so let's start with the engineering and design. The magnets themselves are coils that are in a donut shape. And so they're coils of wire, normally copper wire. They're in a loop shaped in a donut with a smooth metal surface on the top that's pretty seamless. And they have to be connected to struts that hold them in place and also provide a current feed through, so the current can be pumped from outside the machine through the strut into the donut, where it would go around the ring a number of times and then come out the back end. Okay, so that's what we need. Electromagnets are measured in units of amp turns, the number of amps flowing through times the number of turns in the coil. People have built these a couple different ways. Bussard wound his by hand using copper wire, and he ran into problems because every time he turned the machine on, inside the machine, those little copper wires would move because of an electromotive force in play. So after 4 shots, they would touch each other and the machine would short out. So he complained about this in his Google Talk. Mark Stups, who was a hobbyist who built a Polywell in New York City in about 2010, he built a coil winder. He put something together that wound the coils automatically, and he would just feed wire in and wind the coils automatically. If I had a lot of money, to do this experiment, I would probably outsource the coil manufacturing to an entity that could build coils. I'll give you some examples. The National High Magnetic Field Lab is probably the best place in the country to build electromagnets of all kinds, superconducting and non-superconducting. So I would probably look at doing a contract with them where they would build the coils themselves. And the wire could be copper. Eventually it could be superconducting, like a Repco tape. But the issue there is you have to keep it cold, so you'd have to feed in coolant systems through the whole system to keep it cold, liquid nitrogen or liquid helium. That's a problem. Or it could be copper. Now, if you're going to do it in copper, you'd probably want to embed the coil wire in some sort of solid material like a plastic or a wax or a epoxy that would keep the wire from moving around. And there's ways to do this under vacuum that will affix the wire in place. So I would look at that. Now, the whole magnet coil itself needs to be mountable, demountable. They need to be replaceable. You need to be able to swap in a coil, swap out of coil, because over time the coils are going to get damaged. They're going to degrade. They're going to break. You might need to do maintenance on them. So I would order, like, instead of ordering 6 coils, I'd order like 8 or 10 coils. So you have replacements on hand when they break. Okay. And they need to be modular so that they can be swapped in and out, like I said. And your high voltage feed through, you could just wire together, but then you don't need like some sort of interesting interface there. You could just put that together. Okay. Now the coils themselves are mounted to struts, and they can't be mounted to each other. This is an important design change that occurred between 2005, the WB6 machine that Broussard built, and 2013, when the Navy published their great paper in physics of plasma. They got rid of these joints between the coils, and they mounted the coils externally. Okay, this is really important. And the struts themselves probably need to be sufficiently long enough that they don't offer a lot of metal in the center of the reactor. Like I said, the metal struts are a problem because the plasma can touch the metal struts and be conducted away. It's a conduction loss issue that you want to avoid. So you want to make the struts really long so that there's very little metal in the plasma, and you got to keep the space between the rings free of any metal, so that you can allow for material to move through without touching anything, right? Because if you do the models, and Broussard talked about this in his 05 talk at Google, when they modeled the plasma in WB6, they found out that material was traveling along the edge and it was touching the walls. He actually shows a slide of this. Okay, so you want to avoid that in this design. Now, Lockheed had a similar issue with their struts. They used metal struts that held their rings in place inside their machine. And the way they got around the problem was they put an electrostatic charge on the struts that allowed them to, they kind of reduce the amount of material that would touch the struts. So I'd look into something like that as a solution. Now, the other issue is you want to be able to run this machine long enough to get good data. And so far, Polywells have been pulsed. The Lockheed-Martin machine was also pulsed. I'm talking seconds to microseconds to seconds of time where it was running. And the limit wasn't the magnets or the wire. The limit to runtime is the power supply. How long can you feed current to a machine that is power hungry and keep it going so that you can get sufficient data and experimental work? Okay. So Lockheed used supercapacitors or capacitors that could only push off a certain amount of current over a short period of time. EMC2, Broussard's company, back in the 90s, used batteries. They used either car batteries or deep marine batteries. They're like 15-volt batteries. And they would string together a whole bunch of batteries that would supply the current to the machine. The University of Sydney built their own little ad hoc electrical engineering system that did AC to DC conversion, and then they would pump current through their machine that way. Okay, so these are all different power supply options. I want to see a machine run for 2 or 3 minutes of time. And that's a completely different kind of power supply than a pulse power system normally uses. To do that, I would look at three different options. One, I'd look at flywheels. That flywheels have a long history in fusion. The Joint European Torus, when it was built in 1980-81, used giant flywheels to supply its current to run the fusion machine. Flywheels have a specific profile of current versus time where they can supply a decently high current over many minutes of time. And there's a couple commercial off-the-shelf flywheel startups that offer flywheels for these machines. So I would look at flywheels. You don't need a flywheel as large as the one you use on jet, but a smaller version of that for the Polywell would be a good place to look. I would also maybe look at chemical flow batteries. I don't know that field as well, but I know that they have a similar sort of profile where they can release a certain amount of current over time. And if either of those options don't work, I'd also look at TAE Power Systems. TAE is a great fusion company, and to build their fusion reactor, they had to solve these basic problems of how do we supply all this current to our big power-hungry fusion machine from a grid that only supplies 2 megawatts, 1 megawatt. And so they created all these technologies for pulse power capacitors and switches and pulse power over short, compact size and form factors. And now they've turned those all into commercial products that you can now buy. So I would look at buying something from them and using that in the Polywell. But the bottom line is you want to supply enough current to run the rings for minutes, okay? So that covers most of the engineering. Just to add a few other things, for the Polywell, you probably need your own custom vacuum chamber. If you buy a commercial vacuum chamber from, say, Kurt Lesker or somewhere else, you're going to get a cylinder, and that doesn't work for this geometry. EMC2, when they designed this in the past, they envisioned a square box where each wall had externally mounted struts that fed the ring inside it, and then you would seal the thing together in a box. So hopefully I'm showing a CAD of that. So I would look at that sort of geometry. That allows for easy maintenance, and the whole thing is interchangeable, right? Six rings with 6 struts, 6 sets of struts, and 6 walls that are all interchangeable, right? You want interchangeable parts so that you can do ease of operation, ease of maintenance, ease of replacing things if they break, that sort of thing. Just one more thing before I close. I want to mention that the placement of the rings is really important. And if you do a Biot-Savart model of the magnetic field of the rings, and you look at the field in the center of the donut, and in between the donuts at the corners and on the sides, what you find is that the placement of the rings are such that the field in the center is equal to the fields on the sides. I did this model in a blog post in 2010 or 11 where I applied the Biot-Savart law and modeled what would happen as the rings move around, and you see this correlation, which appears to drive how the machine is built and designed, okay? And this kind of makes sense because if you're plasma and you're in the center of this machine, you want to see the same field strength regardless of what direction you go in. It leads to uniformity in the confinement, okay? And that's what drives the overall ring design itself, okay? And the analogy I used for this, or I used in my blog post years ago, was an above-ground pool, okay? An above-ground pool has a uniform height everywhere to hold in water. If there was one side that was lower than the others, all the water would leak out. The same thing is true here with the Polywell. The magnetic field strength is the containing wall that holds in the plasma, and it needs to be uniform regardless of if it's along a cusp line or along the center line. Does that make sense? It should make sense. Okay, so that sums up sort of the engineering and design and construction of these machines. I want to look at the diagnostics, or actually, excuse me, I want to look at the plasma cannons. As I said earlier in the earlier video, the issue is, how do we get plasma into the Polywell that's dense enough to get the diamagnetic effect? Okay, because low density is clearly not going to work. It's going to be magnetized. So they got to get to higher densities to get this effect to work, potentially. And the way MC2 did this was they vaporized a sheet of plastic. Hopefully I'm showing a picture of this. They had an inner cathode, like a finger, and they had a sheet spread out between the finger and the edge. And they pump current along the finger, and that would zoom along the edge of the sheet, vaporize it, sublimate it, turn it into a plasma. And then the plasma would be pushed forward into the reactor. And that created a dense amount of plasma. There are other ways to create dense amounts of hydrogen plasma. One way I would look at is a plasma cannon developed for the plasma liner experiment. Plasma liner experiment's a great fusion machine that's been built at Los Alamos National Laboratory. It was sort of under development starting in the late 2000s or early 2010s under Scott Sue, and they built plasma cannons that are the world's best for this machine. They were built by a company called Hyperjet Technologies in Virginia. Hyperjet is no more, by the way. They changed their name. They moved on to other things, but they have these plasma cannons that are world class, and they can generate a huge amount of plasma in a big chunk and push it out into an open space. And so I would look at that sort of plasma cannon being applied to the Polywell, so that you could create a huge amount of hydrogen plasma and get it into the machine, into the fields where it may create the diamagnetic effect. Maybe, right? So that's one option. There may be other options for creating dense hydrogen plasma, but the goal is to create a lot of hydrogen plasma very quickly and get it into the center of the machine quickly. Okay. So let's look at diagnostics. Our goal here is to image the plasma in some way so that we can get a sort of a picture of this diamagnetic effect if it's occurring, right? If it's occurring, we want to be able to image that. So there's a couple different ways to do it. There's cameras, there's visual cameras in the visible spectrum, in the infrared spectrum, and in the X-ray spectrum. Those three options are all on the table. X-rays, there's a spectrum of X-rays that you can image and a spectrum that you cannot image. The hard X-rays, they go through stuff. It's depending on how high the energy is. So that's an option. Soft X-rays can also be used to image on wax plates. And this is how they do it at the Omega facility at the University of Rochester. When they do an implosion, they have a pack of sheets that are in a container that get exposed to the X-ray emission. And what they get is a series of images, almost like a flip book, that shows how the plasma evolves over time from the soft X-ray emissions from the plasma. And so this is another way that you could image this. Now, I don't know if that would work ideally for the Polywell itself. Just to take a general step back on the Polywell is sort of an intermediate from an ICF implosion or at one extreme or a tokamak run on the other extreme. ICF is high energy very quickly. Tokamak is higher temperatures, but much longer runtime. So the Polywell experiment is somewhere in between the two. And so it's going to need some unique diagnostic, something that's customized for this experiment specifically. A good place to look for customized experimental diagnostics is the flowing pinch experiment at the University of Washington. Uri Shermalock at the University of Washington, for about 15 years, has had a similar problem. He's got a fusion machine that takes longer than an ICF implosion, but not as long as a tokamak. And so he's had to develop his own in-house diagnostics that he calibrates himself for this problem. So the Polywell might want to steal some of this work and apply it to their machine. You know what I mean? Now, on top of all that, there is Thompson scattering, which is where a laser beam is sent into a plasma and you measure the amount of light that goes through, gets reflected, and gets scattered. And based off of that, you can get a measurement of the density of the plasma. Now, Thompson scattering, there's Thompson scattering along a cord, which is just along one beam, or there's Thompson scattering across many, many cords in sort of a two-dimensional XY slice of where there's plasma and there's not plasma. Thompson scattering is great, but it doesn't cover enough area. You could sweep the laser is another option. And if you ran the Polywell for 2 or 3 minutes, that might be enough time to get that, but then you'd have this time evolution over time. So you want repeatability, right? So what I would do is I would fix everything to create a basic standard experiment where you'd inject plasma and get the diamagnetic effect going. And then I would take many, 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 many measurements, but do the same experiment over and over and over again. So just create the same conditions, say 50, 100 times, and collect a lot of data from that and publish all that as one compendium, right? So that's what I would do. Finally, there is flux loops, which is what EMC2 used before. They have fixed a metal loop of material on the inside of their ring to measure a diamagnetic effect. I don't know for sure, but I imagine it's only going to work once the magnetic fields of the rings are shut off. Don't quote me on that, but I think that would be an issue that you'd have to address. Finally, there are Langmuir probes. Now, a Langmuir probe, in the simplest sense, was invented in the 1920s by Irving Langmuir, and it's a hunk of metal. You can think of it like an antenna or a rod that you shove into a plasma. And when you shove it into a plasma, the plasma is absorbed on the rod like a current. And Langmuir probes work by changing the voltage on the rod. You can go from a low voltage to a high voltage, from a negative to a positive. And as you move through all these different voltages, you get an absorption of plasma current. And what emerges is an IV curve. It's called a voltage current curve. It's a signal that can be processed to extract information about the plasma, like its temperature, its energy, its density, where the plasma is relative to the rod, etc. And you could do that over, many different kinds of rods at different depths in the plasma, different lengths. There's even versions where you have 1 rod, 2 rods, 3 rods, or rods in like 16 rods in a quad in a spaced out 4x4 matrix. So lots of options there. I mean, Langmuir probes have been around almost over 75 years. There's a whole industry that has grown up with commercial products that you can buy. There's a great company called Impediance out in England that make Langmuir probes that are pretty good, and they come preset with interpretation data and software and hardware that will interface between the Langmuir probe and the computer. So that's a whole package of product that you can work with there. When it comes to the Polywell, though, you have a problem. The Polywell is a unique magnetic environment. It's not like a stellarator or a tokamak or a mirror machine. Most of the commercial Langmuir probes are set up for tokamaks or stellarators or some version of that. So they have built-in assumptions about the configuration of the magnetic field, the density, etc., that are built into their software. And so you can't just pull an off-the-shelf product and stick it in to your Polywell. You have to make adjustments. And that would be one issue you'd have to tackle. So the University of Sydney, when they did their work, they had to solve a similar problem. They were trying to measure plasma current inside a Polywell with this unique magnetic environment, and it was a problem. It was not easy to do. They actually had to go back to first principles. They had to go all the way back to Irving Langmuir's papers in the 1920s to look up the equations and modify them for the Polywell environment using some assumptions. And they ended up doing a lot of mathematical jumping jacks to deal with all this. And there's a great paper from 2010. I think the work was done by Matt Carr and Joe Kashin that talks about all this. And I wrote a blog post about this that I think it's called The Fierce Urgency of Now. If you want to look it up, it's on my GitHub. But it'll walk you through all the math that they did. It was a lot of complicated math. Langmuir probes are inherently complicated. Normally, the user doesn't see any of that because the software is already written for them that kind of deals with all that. They don't have to deal with the math. But in University of Sydney's case, they actually had to go back and deal with all the math. But they did all that, and they also calibrated the probe. They used a calibration stand. They ran a known current, so they knew what the solution would be, and they calibrated the probe over a given current. So anyway, if you're doing a Langmuir probe and a Polywell, you have to deal with all these issues. These are all sub-issues, but you have to deal with all these problems. But anyway, that's the one thing you could do. So then you could get a measurement of the plasma by physically sticking a piece of metal into the machine and measuring the current. So given all these diagnostics, what I would do is I would try to image the plasma in a diamagnetic trap. And I would try to measure the amount of material leaking through the cusp. So how much material is actually leaking through the cusp? How much material is leaving through the skin of the wiffle ball, in fact, if it's occurring at all? What is the overall shape of the plasma? I don't think we actually really know for sure what it's going to take. I mean, models have suggested that it'll look like some sort of star shape where the points of the star line up with the cusps of the field. And then if it swells up sufficiently, that star shape would transition to more of a spherical shape. But I don't think these things are, we don't have data or pictures or photographs or x-rays or any kind of image of the plasma doing all this behavior. So that's what we want. That's what we want to see. So, and again, Lockheed may have already done this. They may have already done all this stuff. And if they did, they need to publish because we need to see it in a peer-reviewed paper. We can't have this data locked up, not helping anyone, especially if they called it a dead end, if it came to a dead end. Anyway, that's what I would do. And then once that's done, I publish multiple journal articles in a peer-reviewed paper that explore all this in open literature so that everyone can deal with it. From that point forward, you could look at benchmarking models of the Polywell using raw experimental data pulled from this machine. So you'd want to benchmark models, and the modeling would allow you then to explore 6 rings, 12 rings, 24 rings, other ring configurations. So that's all useful. And you could look at what would happen if you made the plasma mostly negative. How likely is it to create a potential well inside that? Okay. All right. Thank you so much for your time. I'd love to see this experimental design built and tested. Budget wise, I think you'd probably need on the order of 5 to 10 million over several years. You'd want a good team. I think 10 to 20 people would be appropriate. And you'd want people that are qualified to do the job, that know the job, and are really, embedded with the spirit of let's get this done, let's get this measured. And you'd want to do it openly as possible for the benefit of the fusion community and the physics community more broadly. So that's what I would love to see happen. And I think it would take several, 1 to 3 years to get that kind of effort up and running. But that's what I want to see. Okay. Thanks a lot. Take care. Bye.